So in this lecture, I will present the Helly-Bray theorem. The theorem reads as follows. Assume that you have a sequence of probability measures μn defined on R which converge weakly to a probability measure mu. I claim that this happens if and only if for any continuous function b which is bounded. So let me represent by CBR the set of bounded continuous functions defined on R. So if and only if for any such function the interval of f d mu n converge to f d mu. So let's prove this theorem. So first assume that mu n converge to mu weakly, and then I will prove the converse. So let's assume that mu n converge to mu weakly, and let's fix a function f which is continuous and bounded. Now we want to estimate this difference. To estimate this difference, I will fix some epsilon positive and show that this difference is bounded by epsilon if n is very large. I will need to introduce some quantities here that will be used later. So for that fixed delta, first I will find points a less than b in R, which are continuity points of f. So I require them to be continuity points of f, and f will represent the distribution function of the probability measure mu, and fn the distribution functions of the measure mu n. So let me take a and b continuity points of f, and such that the measure of the interval ab, open at a, closed at b, complement, it's bounded by epsilon. I claim that this is always possible, and let me explain why. First, it's always possible to find a and b for which the measure of the complement, which means the measure of the union of this interval with that interval, closed and open, it's bounded by epsilon. What might happen is that a or b, or maybe both, are not continuity points. But we have seen that the set of points in which the distribution function is not continuous is at most countable. So if a and b are not continuity points, we can always replace b by a b prime and a larger than b and a prime smaller than a, which are continuity points. And of course, this inequality will be preserved. So it's always possible to find continuity points a and b of f for which the measure of the complement of the interval ab is bounded by epsilon. So this defines a and b. Note that epsilon does not appear in the notation, but a and b depend, of course, on epsilon. Then, once I have epsilon and ab, let me consider the interval a minus 1, b plus 1. Well, this is a compact interval. F, it's a continuous function, so it's uniformly continuous on this interval. This means that for that given epsilon, I can find a strictly positive delta such that, well, if x and y belong to this interval, so to the interval a minus 1, b plus 1, and if the distance between x and y it's bounded by delta, then fx minus fy it's bounded by epsilon. So the uniform continuity of f on the interval a minus 1 b plus 1 guarantees the existence of this delta. The last quantity which I want to introduce is the L infinity norm of f. So let me denote by m the L infinity norm of the function f, and I will now erase the board and start again just keep in mind the definition of A and B, delta and M, which will be needed later. So I just recall here the notation. We are proving that if Mn is converging weakly to mu, then f d mu n is converging to f d mu, where f it's a continuous bounded function. And we fixed epsilon, we introduced A and B, which are continuity points, M and delta. Now I want to estimate this difference. And what we will do is we'll divide these intervals on 3 intervals and estimate each one of them separately. So I will say that this is bounded by I1n plus I2n plus I3n. I1n, it's simply the same expression, but now taken in the interval minus infinity a. F d mu. So this is I1n. I3n and I2n are exactly the same expressions, but with different intervals. So let me tell you that I2n is the one we get replacing in this difference this interval by the interval AB, and I3n the same expression in which we replace this interval by the interval b plus infinity. And I will estimate separately I1, I2, and I3. I will start now with I1n. So I1n is this expression, and here the estimation is very simple, because I will just estimate this difference by the sum Fn d mu, f d mu n, plus a similar expression with mu instead of mu n. And now I will estimate each of these expressions by the bound I have on f, which is the L infinity norm of f, which is m, mu n minus infinity a, plus m mu minus infinity a. But recall, I'm representing by fn and f the distribution function associated to the measure mu n and to the measure mu. So this is exactly equal to m fn a plus m fa. But now mind, a was defined in such a way that the measure of the complement of this interval is bounded by epsilon. Therefore, the measure of this set, which is f of a, it's bounded by epsilon. So this expression here, it's bounded by m times epsilon. And the second one, since a, it's a continuity point of the distribution function f, since mu n converge weakly to mu, f and a converge to f of a, which is bounded by epsilon. So this tells me we just proved that the limit sup in n of y1n, it's bounded by 2 times epsilon times n. 2 times epsilon times n. So this is the estimate of the first part. Now I will turn to the estimate of the third part, which is exactly the same, and then consider the second piece. So for the third part, and the argument it's essentially the same. So now remember the third part was b plus infinity and b plus infinity. Let me go slightly faster just by estimating this expression by m times mu n b plus infinity plus m times mu b plus infinity. Now, again, here I can express the measure of this set, this interval in terms of the distribution function. It's equal to m times 1 minus fnb plus m times 1 minus fb. Now this is the measure of that interval, and we have seen that the measure of this interval is bounded by epsilon. So again, this expression, as before, it's bounded by epsilon times n, while this one, b, is a continuity point of the distribution function f, and since mu n converge weakly to mu, f and b converge to fb. So this quantity here converge to m times 1 minus fb, and we have seen that this quantity is bounded by epsilon. Therefore, we just proved the same bound for the third piece, which is that the limit sup of I3n is also bounded by 2 epsilon n. So up to now, we estimated the first and the third piece, and the limit sup of the sum is bounded by 4 epsilon m. It remains to estimate the second piece. So the second piece, I2n, it's given by this difference. In order to estimate this difference, so here is A, here is B, and remember that we have fixed a delta in which f is uniform. By using the uniform continuity of the function f, we obtained this delta, which has this property. So I will define a sequence of points t0 being equal to A. Now to get t1, what I will do is I will here obtain t0 plus delta and t0 plus delta over 2. So in this interval, I will choose one point which is a continuity point of the distribution function f. So t1, it's a point which is in the interval t0 plus delta over 2 and t0 plus delta, which is a continuity point of the distribution function f. So that's a continuity point of f. And I will proceed in this way. So assume that you created tj. You consider the 2 points, tj plus delta and tj plus delta over 2, and you choose in this interval, open on both sides, a point which you call tj plus 1. So this point belongs to this interval, and this point has the property that it is a continuity point of the distribution function f. And you continue in this way until you find a point tn, and I'm calling that point, that index n. Well, this point tn has the property that its distance to b, it's smaller than delta, strictly smaller. So tn, it's plus delta, it's strictly larger than b. So in this way, you constructed a sequence in which the first point, it's equal to a, second point t1 up to the n point, and tn plus 1, let me call tn plus 1 this point b. The property of this sequence is that, well, remember that a and b are continuity points of the distribution f, and by construction t1 up to t1 are also continuity points. So all these points are continuity points of the distribution f, and also the distance between two consecutive points, it's bounded by delta. So tj plus 1 minus tj, this is strictly bounded by delta. So we are exactly under the assumption of this condition. The points belong to this interval, their distance is bounded by delta, and therefore ftj plus 1 minus ftj, it's bounded by epsilon. Actually, any point inside this interval will satisfy this condition. Now, once you introduce all these points, we are able to estimate this quantity. The first thing we will do is to replace this integral as a sum between 0 and n of the integrals in the intervals tj, tj plus 1. And the same thing in the other side. In the other integral. So we divided the interval AB in these small intervals tj, tj plus 1. Now, what we do is that we will compare ft with ftj. So I will subtract and add ftj. Now I have two pieces. The first one consists in the difference between ft minus ftj. So I will estimate this one, and then I will estimate the second one. For the first one, so forget about this term. What we have is this, and the same expression here. And what I will do is just bound this expression by the absolute value of this difference. So we have the sum of the integrals between tj, tj plus 1 of ft minus ftj mu dt. And a similar expression with mu n instead, with mu instead of mu n. Now, since t belongs to the interval tj, tj plus 1, and the distance between tj plus 1 and tj is bounded by delta, this means that these conditions are satisfied for t and tj, and therefore the difference between ft and ftj is bounded by epsilon. So this quantity here, it's bounded by epsilon, and what we get by summing over this interval is that this quantity, it's bounded by epsilon. Well, here we are simply adding the measures of these intervals, and these intervals add up to the interval AB. So this is bounded by mu n AB, but mu n, it's a probability measure, and therefore this expression, it's bounded by epsilon. So this expression, it's bounded by epsilon, and the same thing happened for this expression, in which I take ft minus ftj. So I get 2 epsilon from this argument, and what I need still to estimate is this integral with ftj instead of f. So let me just recall that I have still a 2 epsilon coming from this argument, and now I need to estimate the following quantity, in which I replace now ft by ftj. Well, now this is a constant, so actually what we have is that this is bounded by the sum of ftj, and what I have here is the measure mu n of the interval tj, tj plus 1 minus the measure of the interval tj, tj plus 1. I can express these measures in terms of the distribution function. This is nothing more but then the fn tj plus 1 minus fn tj minus, so I get minus f tj plus 1 plus f tj. And since all tj's are continuity point of the distribution function, and since mu n is converging to mu, as n converge to infinity, fn tj plus 1 converge to ftj plus 1, and fn tj converge to ftj as well. Therefore, this quantity, as n converge to plus infinity, as small n converge to plus infinity, converge to 0, because n is fixed. Delta is fixed in this. So we just proved that the limit sup of E to n it's bounded by 2 epsilon. And since we have proved that the limit sup of E1 and E3 n were bounded by, if I recall correctly, bounded by 2m each one, so I1 and I3, what we get from this argument is that the limit sup, as n goes to infinity, of f d mu n minus f d mu, that this is bounded by 2 times plus 2 plus 4m times epsilon. And since this is true for every epsilon, this proves that indeed f d mu n converge to f d mu, and completes the proof that if a sequence of probability measure mu n converge weakly to mu, then the integrals of any bounded continuous functions converge to the integral of that bounded continuous function. So just a remark, I've been very careful here by writing, let's say, AB f d mu n, so by or d mu. So by explaining that we are taking this set open at A and closed at B, this interval, and note that this indeed it's different from AB f d mu n, d mu, just because maybe m puts some positive mass on B. So let's say that, for instance, if mu is the Dirac mass at B, while this is equal to 0, that would be equal to Fb. So in contrast with Lebesgue measure, it's very important to say if you're including the endpoint in the domain of integration or not. So for these reasons, you should be very careful. This is why I always write in the integrals in this way. Now, let's prove the converse. So let's assume that for all functions which are continuous and bounded in R, we know that f d mu n converges to f d mu. And I want to conclude from that mu n converge to mu weakly. So let's prove this claim. And to prove that, let's fix x in R, a continuity point of f. And what we have to prove is that fnx converge to fx. But what is fnx? Fnx is the measure of the interval minus infinity x, which is also the integral of the indicator function of the interval minus infinity x of d mu n. So what we will do here is that we will bound below and above this indicator function by continuous function. So fix an epsilon positive. We know that x, it's a continuity point. So x, it's a continuity point. So let's say here it's x. And let's estimate, so for that fixed epsilon, since f is a continuity point, there exists a delta such that if y minus x is less than delta, then fy minus fx it's bounded by epsilon. But actually, since f is a monotone increasing function, what this is saying is that, well, fx plus delta it's bounded by fx plus epsilon, and that fx minus delta it's larger than fx minus epsilon. So these are the two bounds. So we obtained delta such that if this point it's x plus delta and this point it's x minus delta, then the function at x, and here is fx, this distance between fx and fx plus delta it's bounded by epsilon, and similarly this distance it's bounded by epsilon. So now what we will do, as I said, we have an indicator function. This indicator function, it's simply the indicator function of the interval minus infinity x, so it's equal to 1 up to x, and it's 0 from x to plus infinity, so it's closed at x, so it's 1 up to x and then 0 from this point on. So we will estimate this function, which is discontinuous at x, by two continuous functions, one which is above f and the other one above this indicator function, and the other one which is below. So let me take this function and this function. So here's one function which is equal to 1 up to x minus delta, and then it's linear and equal to 0 starting from x, and the other one which is equal to 1 up to x and then linear from x to x plus delta and 0 at x plus delta, and from that point on it's equal to 0. So let me call, let's say, the first function f epsilon and the second function g epsilon, and what I know is that f epsilon and g epsilon, well, they are continuous functions and they are bounded, so they belong to the space of bounded continuous functions, and also that f epsilon it's bounded by the indicator of minus infinity x, and this indicator it's also bounded above by g epsilon. So now we have, from this we conclude that f epsilon d mu n it's less or equal than the integral of this indicator function with respect to mu n, but this is f n x. And the integral of this indicator function with respect to mu n gives you f n x, and this is bounded by g epsilon d mu n. Now, since f epsilon it's a bounded continuous function, we know by assumption that this expression is converging to, so the left hand side, let me write it here, it's converging to f d mu. So f d mu, it's less or equal than the limit inf of f and x, which is bounded by the limit sup of f and x, and this is bounded by g epsilon. So there is an epsilon here, and g epsilon d mu. Because, again, since g epsilon is a continuous bounded function, this integral by assumption is converging to that. So now what remains to be done is to estimate g epsilon and the integral of f epsilon But that's very easy because, well, g epsilon, let's start with g epsilon. G epsilon, it's this function which is 1 up to x and then linearly decreasing up to 0 at the point x plus delta. It's clearly bounded by this function. So the indicator function, so g epsilon, it's bounded by the indicator function of minus infinity x plus delta. Well, because just you see the picture, and therefore the integral of g epsilon d mu, it's bounded by the integral of this indicator function, but the integral of this indicator function, it's exactly equal to fx plus delta. And fx plus delta, we have seen, it's bounded by fx plus epsilon. So I will not write it, but you have this bound. And we do the same thing on the left-hand side. You see that f epsilon, it's equal to 1 up to x minus delta, and then it's non-negative. This means that f epsilon, it's bounded below by the indicator function of minus into the interval minus infinity x minus delta. And now if you take the integral of f epsilon with respect to mu, so it's bounded below by the integral of this indicator function with respect to mu, and the integral, it's equal, so this is larger than f at the point x minus delta. And now fx minus delta, it's bounded below by fx minus epsilon. And, well, let me write it, that this is bounded above by fx plus epsilon. So you see that the limit inf, it's bounded below by fx minus epsilon, the limit sup, it's bounded above by fx plus epsilon. This is true for all epsilon, so if you send epsilon to 0, what you get is that f and x converge and converge to fx, and this is exactly what we wanted to prove. So we just proved the main statement of this lecture. Now in the remaining part of this lecture, I want to compare convergence in distribution. So a sequence xn converging in distribution to x with a sequence xn converging in S in probability. And my first lemma states the following: assume that you have a sequence of random variables converging in probability to x. What I claimed is that then it converges in distribution to x. And I leave it to you as an exercise to fill the details of the following proof. Assume that, therefore, that you have this sequence xn converging in probability to x. You want to prove that xn converge in distribution to x. Let's call fn and f the respective distribution functions of xn and f. Let's take a point x, a continuity point of the function f. You want to show that f and x converge to fx. What you know is that xn converge in probability, so this means that the probability that xn minus x larger than eta, say, converge to 0 for all eta positive. So this is convergence in probability. And now, well, let's take f and x. Since f is continuous at the point x, you fix an epsilon. And again, as in the previous proof, in the second part of the previous proof, you can find the delta so that strictly positive delta, so that fx plus delta, it's less or equal than fx plus epsilon, and fx minus delta, it's larger than fx minus epsilon. So for that fixed epsilon, you find delta. Now you want to use this quantity, and you take the probability that xn it's less or equal than x. You want to estimate this quantity. You want to show that this quantity converges to this one by using this. So you want a lower bound and an upper bound. Let's say that let me show you how to prove an upper bound. You would say that this is bounded by the probability that xn less or equal than x, and the difference between x and it's bounded by delta. So the delta is this delta plus the probability that xn minus x it's larger than delta. To get a lower bound for that, here we have an upper bound. To get a lower bound, you just plug this quantity inside the probability. So the same argument will provide you a lower bound. So now, since xn converges to x in probability, this term here is converging to 0 as n goes to infinity. While for that one, well, if you know that xn is bounded by x and the difference between xn and x is bounded by epsilon, this means that x is bounded by x plus delta. So this is bounded. So this set is contained in the set where x is bounded by x plus delta, and this is less or equal than fx. Well, this is equal by definition of fx plus delta, and this is less or equal than fx plus epsilon. So this is fnx, and this tells you that the limit sup of fnx is bounded by fx plus epsilon, and as I said, the same argument will provide you the lower bound, and so that gives you a first proof that indeed convergence in probability entails convergence in distribution. Maybe I didn't give you all details in this proof. I ask you as an exercise to fill the details of this argument. Let me give you a second proof of this result by using Helly-Bray's theorem. So what we have to show is that the expectation of fxn converges to the expectation of fx for all f bounded and continuous. So let's fix such a function f, and let's prove this. So let me call this sequence an, and I want to prove that this sequence an converges to this quantity. So in order to prove that the sequence an converges to a, well, this sequence an it's bounded because f is a bounded function. So we have a bounded function, bounded sequence an, and we want to show that an converges to a. So what we have to prove is that for all subsequence nk, there exists a sub-subsequence nkj such that ankj converge to a. So this is, if we are able to prove that for any subsequence there exists a sub-subsequence which converges to a, then the sequence itself converges to a. So let's take here a subsequence nk, and what we want to do is to obtain a subsequence in which converge to this expression, right? So we have here the sequence x and k. Since xn is converging in probability, x and k it's converging in probability to x. And we have seen that if we have a sequence converging in probability to a random variable x, we can find a sub-subsequence which converge almost surely to x. So that given any subsequence nk, as the original one converge in probability, the subsequence also converge in probability, and we have seen, therefore, that it possesses a sub-subsequence which converge almost surely. Now, since x and k, j is converging almost surely, and f it's a bounded continuous function, first you get that f x n k j it's converging to f x almost surely, because f is continuous. So if this sequence, if you take an omega for which this one converges to that one by continuity, you get this convergence. Since this happens almost surely, this one happens almost surely. And therefore, if you take the expectation by the dominate convergence theorem, this expectation converges to fx. And this is exactly what we wanted to prove. We wanted to prove that any subsequence possesses sub-subsequence which converge. And this is exactly what we proved by using this result already proved. So that provides a second proof of the fact that convergence of probability is stronger than convergence in distribution. The converse is false. So it's not true that if xn converges to x in distribution, then xn converges to x in probability. So I ask you to find an example in which of a sequence which converges in distribution and which does not converge in probability. However, we have the following result, which tells us that if xn is converging to a real number in distribution, so a real number, it's a random variable which takes only one value, then indeed xn converges to C in probability. So C here, it's a real number, and we are assuming that this sequence converges in distribution to C. So proof. Well, what we know is that f of x, n, so if I represent by fn the distribution function of the random variable xn, that fn is converging to the distribution, let me call it f, c of x, for all continuity points. So fc represents the distribution function of the constant c, and since it converges in distribution, this is true for all x continuity point of fc. But what is fc? Well, the distribution fc, it's right continuous, so it's equal to 1 starting from x, and it's equal to 0 up to x. So this is the distribution function associated to the constant c. So now you fix an epsilon, and what we want to prove is that the probability that xn minus c larger than delta, larger than epsilon, this is converged to 0. This is what we need to prove in order to show that xn converges in probability to c. But this is equal, so for the probability that xn, the absolute value of xn minus c is larger than epsilon, so what we are doing here, we are taking an interval of size epsilon, so c minus epsilon and c plus epsilon, and we are asking what is the probability that xn lies outside this interval. So this is equal to the probability that xn is larger than c plus epsilon plus the probability that xn is smaller than c minus epsilon. Well, the probability that xn is larger than c plus epsilon, it's 1 minus fn of c plus epsilon. And the probability that xn is smaller than c minus epsilon, it's bounded by the probability that xn is less or equal than c minus epsilon, and this is fn c minus epsilon. Now you see that if epsilon is positive, c plus epsilon and c minus epsilon are continuity points of f. And therefore we can pass to the limit and say that as n goes to infinity, this expression is converging to 1 minus fc of c plus epsilon plus fc minus epsilon. But now at c plus epsilon, fc is equal, so this is fc is equal to 1, and at c minus epsilon, fc is equal to 0, so this is 1 and this is 0, and therefore this quantity is equal to 0, and therefore we proved that for any epsilon, this quantity is converging to 0, and therefore that xn is converging to c in probability. So you see, though it's not true that convergence in distribution entails convergence in probability, if xn is converging in distribution to a constant, then it converges also in probability. Now, let's prove the last lemma of this lecture. Let's assume that we have xn, a sequence which is converging in distribution to a random variable x, and yn, a sequence which is converging in distribution but to a constant c. And what I claim is that then xn plus yn converge to x plus c. And I want you also to think of an example in which we have two sequences, xn converging to x in distribution, yn converging to y in distribution, and it's not true that xn plus yn converge to x plus y. But in the case in which yn converge to a constant, so again here c represents a real number, it's true that the sum converge also in distribution to x plus c. So let's prove this result. Let's fix a function f which is bounded and continuous, and what we need to show is that the expectation of f xn plus yn converge to the expectation of f x plus c. What I claim is that it's enough to bound to show that the difference between f xn plus yn and the expectation of f of xn plus c converge to 0. So it's enough to prove that this converges to 0, because if this converges to 0, in order to prove that, we have to show that this sequence converges to that one. But it's clear that if I define the function gc of x as fx plus c, this sequence, this function gc is continuous and bounded. Therefore, since xn is converging in distribution to x, the expectation of gc xn converges to the expectation gc of x. Therefore, the expectation of f xn plus c converges to the expectation of f plus c. So what we really need to prove is that this quantity here is going to 0. Now, for that, well, again, we will have to introduce certain quantities which will play a role. The first one is that, well, we know that given, so I want to show that this is bounded by epsilon. So let's fix an epsilon. Now, for that epsilon fixed, since x is a random variable, I can find a less than b. These are continuity points of the distribution of x, which now I'm representing by fx, and such that the measure of the complement of AB, it's bounded by epsilon. So I want to find continuity points of fx, AB, such that this measure it's bounded by epsilon. Once I have that, let me look at the interval a minus 1 and b plus 1. Now, since this function f, it's uniformly continuous, let me, there exists, given that epsilon, there exists a delta such that if x minus y, it's bounded by delta, and x and y belongs, well, I won't need that interval, but that interval scaled by c, so the interval a plus c minus 1, b plus c plus 1. So if x and y are distance delta, and if they belong to this interval, then fx minus fy, it's bounded by epsilon. So let's, so I introduced AB, and now I introduce delta, and with these two quantities, I will be able to estimate this expression. So what we will do here is to consider f xn plus yn. Now I'll start to introduce indicator functions. So the first one is that yn is not very far from c. So let's say that yn minus c is at a distance less than delta. And once I introduce this one, I have to bound the complement, but the complement I will just bound. So I'm considering this expectation. I'll perform the same with the second expectation, but consider this expectation, introduce this indicator and the indicator of the complement. I will estimate the indicator of the complement by saying that, well, f is bounded by its L infinity norm, which I'm calling m. So let's call m the L infinity norm of f. So f is bounded by m, and this quantity, it's the probability that yn minus c is larger than delta, but this we know that converges to 0 because since yn is converging distribution, converging probability. So I can say that the second piece converges to 0 as n goes to infinity. So as n goes to infinity, the second piece, the piece in which it's larger than delta, converges to 0. So now I know that yn minus c, it's bounded by delta. Let me compare this with fxn plus c. And for that, I will need xn to be in this interval. So let's assume that xn belongs to the interval AB. And always. So here, before I introduce this quantity, let me introduce now the indicator that xn does not belong to AB and that xn belongs to AB. So the case in which xn belongs to AB, I will bound this expectation, this f, by the L infinity norm, m, and it will remain the probability that xn does not belong to AB, and this quantity converges to 0, because the probability that xn does not belong to AB it's bounded by, well, either it belongs to minus infinity a, and this is actually, it's equal to fn a, plus the probability that it's larger than b, and this is 1 minus fn b. Now, since a and b are continuity points, I can send n to infinity to get that this converges to Fa, this converges to 1 minus Fb, and this is bounded by epsilon, so this quantity here, it's bounded by epsilon in the limit. So I have a second quantity which it's of the order of epsilon when I send n to infinity. So I can introduce the indicator function of the complement. So I can assume that xn is in AB. Now, since xn is in AB and yn minus c it's bounded by epsilon, this difference between xn, so this difference, it's xn plus yn minus xn plus c. In this set, it's bounded by delta. So this first condition is satisfied. Now, xn plus yn is at a distance delta from c, so xn plus yn it's bounded by xn plus c plus delta, and it's bounded below by xn minus plus c minus delta. And xn, it's in AB, so this quantity is bounded by b plus c plus delta, and this quantity is bounded by a plus c minus delta. So under these two conditions, I know that xn plus yn belongs to the interval a plus c minus delta and b plus c plus delta. So if I take delta smaller than 1, which I can always do, I have that there exists a delta which satisfies this. If delta is larger than 1, I can take it equal to 1. It will still satisfy this condition. So if I take a delta smaller than 1, what I get is that xn plus yn belongs to the interval a plus c minus 1, b plus c plus 1. So it indeed satisfies the second condition, and the same thing for xn plus c. xn plus c, since xn belongs to the interval ab, will belong to the interval a plus c, b plus c. So since in this interval, if these two conditions are satisfied, this difference is bounded by epsilon, this means that this condition is bounded by epsilon, and therefore I get an extra epsilon term, and this shows that actually this quantity minus this quantity multiplied by these two indicator functions, it's bounded by epsilon. So I can replace, after I introduced these two indicator functions, I can replace this quantity by that quantity by paying a price of order epsilon. So after I performed this replacement, well, I'm done, because I can do the same procedure here, and by that I mean introducing this indicator function and this indicator function by paying extra costs given by these two first, and therefore transform this expectation in this expectation with these two indicator functions, but this is exactly what I obtained from the left-hand side. So once I introduced this indicator function and replaced xn plus yn by xn plus c, I'm done. And this proves that indeed this difference converges to 0 as n goes to infinity. So I think I went too fast here, but the proof is really very close to the proof which I presented at the beginning of this lecture, and so I think you won't have any difficulty in filling the gaps which I didn't left any gap, but I went fast. So I think you can understand what is the argument. And finally, let me leave you as an exercise the following lemma. Again, I assume that xn is converging distribution to a random variable x. that yn is converging in distribution to a real number c, and what I want you to prove is that if I take the product xn, yn, this is converging in distribution to c times x. So the proof goes exactly as I said, as I presented before, in the sum, in the case in which we have a sum instead of the product. And so I leave it to you as an exercise. And once you have these two results, it's clear that if you have yn, zn random variables in which yn is converging in distribution to a random number a, zn converging in distribution to a random number b, and xn a random variable converging to x, everything here in distribution, then it follows by the previous results that yn, xn plus zn, it's converging in distribution to a, x plus b. Right, and with this result, I will finish this lecture.